Hello everyone, welcome back to my YouTube channel. Today we will be discuss on Bragg's law and X-ray diffraction. Myself Anima Ghosh, Associate Professor of Physics. So today we will discuss what is X-ray diffraction, how Bragg's law derive his famous equation, mathematical derivation of Bragg's law, physical meaning of each terms, and how we can use it to solve or to find out the distance of the planar distance or the angle between two planes to X-ray planes and how it used in real materials research. So first, that what is this X-ray? Why we use it? Why you need it? So, have you ever wondered how scientists determine the atomic structure of crystals? In our previous discussion, we have discussed that in an atom, in a crystal, how the atoms are sitting and how they are bonding is correlate to each other, and about their orientation and crystallinity or their arrangement of the atom we have discussed. So another thing is how do we know the arrangement of atom uh, inside materials like silicon or NaCl or graphene. We cannot see the atom directly with ordinary microscope. So how we can do this? How we can see the atoms? So the answer is the X-ray diffraction. So it is the tool to find out the atoms, their atomic structure, phase, properties of these atoms inside it. So today this X-ray diffraction is beautifully explained by the Bragg's law. So today we will discuss the Bragg's law, fundamentals of its, and we will find out that what is the physical meaning of each of these terms and how we can use it in real materials. So let's begin. The first is that what is X-ray? X-ray are we frequently use this word that we need to do the X-ray. We need to do this. So what is this X-ray? X-ray is basically the electromagnetic radiation. So let's begin that what is X-ray? X-ray is the electromagnetic radiation known as X-ray. It have the wavelength of roughly 0.1 angstrom to 100 angstrom. So when it discovered, X-ray were discovered by Roentgen 1895. X-ray are the electromagnetic waves of shorter wavelength in the range of uh, roughly 0.1 to 100 angstrom. So the longer wavelength in the spectrum is known as the soft X-ray and the shorter wavelength known as the hard X-ray. So the longer wavelength end of the spectrum, that means wavelength lambda, when it is longer, we can say them soft X-ray, and if the shorter wavelength, this lambda is the shorter, those are hard X-ray. So now think is that why do we use X-ray? So because the scale minor, the interatomic distance in a crystal is basically this in the range of 0.1 angstrom to 100. This is the atomic structure, and interatomic distance between two atoms is roughly this, and the X-ray naturally diffract when incident on the crystal material. So as we say that the X-ray is the electromagnetic wave, and we can say that having its range means this phase to this, it is roughly 0.1 to 100 angstrom. So this range and this interatomic distance is almost equal, so the X-ray can be used to detect it. So for diffraction to occur, the wavelength of radiation must be comparable to the spacing between objects. So visible light have wavelength around of, we know that in around 10 power of minus 7 meter. So but X-ray having the wavelength of around 10 power of minus 10. So this is perfectly matching. This is why X-ray are used to study the crystal structure. So now moving forward, that what is concept of crystal plane, and what are how we can unlock the secret of this crystalline material inside the properties. So in crystal, basically atoms are arranged periodically in 3D space. We imagine the imaginary planes passing through atoms. These planes are separated by distance, that is called as d-spacing. The distance is very important in Bragg's law. So the X-ray diffraction is used here to know the reverse by engineering unknown materials and quantify the precise structural parameters. What are those? Those are identify phases. We know there are crystal structure of 14 different Bravis lattice of 7 crystal types. So identification is very important to explore the properties, either it is cubic or monoclinic or hexagonal or others, and quantifying the cell parameters. So next is quantifying the changes in cell parameters. So while we are identifying the phase, and we are going for cubic to tetragonal, so that we know generally in the cubic all the A, B and C, A is equal to B is equal to C. However, in the tetragonal, A is equal to B, not equal to C. So these are the differences from one phases or one crystal structure to another. So this is another important parameter to know, to explore the structural parameters and determining the orientation. So we had discussed in our previous one lecture that the orientation of the atoms inside the crystal may or may not always be the same. So it is important to know. And third is the measure the crystalline size. Thus with size we can see that it having the dimension from the nano to 3 dimensions. So measuring depends on the crystalline size, since the properties is hugely varied. So it is very important to know about the crystalline property. So solve the complete crystallographic structure, like it is have a complex structure. So the cell parameter, phase group, atomic structure of noble or unknown crystalline materials. So these are the important parameters to know. And how we can know? We can know this from the X-ray diffraction. So the X-ray get diffracted when they are allowed to incident on crystals. So X-ray diffraction is here an important tool used to identify the phase, quantifying the changes in cell parameters, orientation of the structure, crystalline size, and the other structural parameter. It is also used to determine the crystallographic structure like cell parameter, phase group, atomic coordination of noble or unknown crystal materials. So now we'll be directly move towards the Bragg's law. So in 1912, the breakthrough by W.H. Bragg and W.L. Bragg, the W.H. scientist W.H. Bragg and W.L. Bragg discovered that X-ray can be regularly reflected by the planes of the crystals. They successfully derive the mathematical relation that link the incoming light to the interstructure of the material. So what are the that in let's say this is a crystal structure and some light is coming here. So once these lights are coming, their diffraction, which angle they are coming, and in the separation of the atomic, their interplanar dashing d. So they are established, or their mathematical this relation is give that the link that incoming light to the internal structure of the material. So the relation of the wavelength of X-ray, angular position of scattered beam, and the separation of atomic plane, this is called the Bragg's law. So now let us derive the Bragg's law step by step. So first of all, define the crystal lattice and interplanar space. So consider a crystal made up of equidistant parallel plane of atoms. So you can see here in plane 1, these are the atoms are sitting here in a equivalent distance, and they are in a equidistance, and the plane 2. So here also the atoms are in a equidistance, and also they are in parallel plane. So the distance between the plane 1 and this plane 2 defined as the d. So the let us move forward that when the monochromatic X-ray interact the atomic plane, so when the rays are comes to this plane, what will affect? So let's say that monochromatic X-ray beam of wavelength lambda falls at an incident angle theta on this atomic plane. So as the beam hits, so these are the monochromatic X-ray hitting the atoms of this plane. So as the beams hits, each individual atom scatters the X-ray outward in all direction. So here one more consideration is that one ray reflects from the top plane, and another ray penetrates the deeper and reflects from the lower plane. So this some rays, let's say it is coming here and then they will reflect back here, but some rays go penetrating more and coming to the deeper, and so this deeper means here we are considering as plane 1 to plane 2. So coming here and then they are diffracting. So then what will happen? So let's say that in most of the this direction, the scattered X-ray experience the destructive interference and cancel out. However, in certain specific direction, the scattered radiation are perfectly in phase. So they interference constructively to produce an intense and measurable spot. So what is constructive interference and destructive interference? That while these similar rays are coming, means they are in a same phase. See here this positive part and here this positive path, both are in a same phase. So when they both are superimposed, they can produced the constructive interference, and in case of destructive interference, the phase, this is in positive side, this this part in positive side, however this in negative, so they are in opposite phase. So when they superimpose and then they produce, so they can produce the destructive interference. So now moving forwards, that the how this Bragg's law concept is coming. So now the geometry path of two parallel ray. So let us consider that two specific X-ray. One is PA and another is QB. So they are coming, and one is hitting in the plane 1 at atom A, and the another ray QB that is hitting in bit deeper plane. So let's say this is plane B and at atom B, and they are reflecting it back in this direction AR and BS respectively. So the X-ray of this QB reflects at B in the direction of BS from the second plane, and you know here the distance is the D, and the angle, when the ray is hitting this atom, the angle between the incident ray and the plane, that is the theta. So according to Bragg's law, the relations of in theta, d, and order of reflection. So the formula can be written as 2d sine theta So formula is 2d sine theta is equal to n lambda. D, we already familiar with the D. D is the interplanar distance. So distance between plane 1 and plane 2. Theta is the sine theta. Theta is the angle of incident ray with respect to the plane. And n is the n stands for 1, starting from 1, 2, 3. So this is 1 is for first order, second order, third order reflection respectively, and lambda is the wavelength of light. So this 2d sine theta is n lambda. This is called the Bragg's law. So now will we prove this one, this mathematical description, mathematical explanation of this Bragg's law. That let us consider the X-ray PA and X-ray PA falls on the atom A, and then after reflection in going to the path AR, and another ray QB that coming to the B hitting at plane 2 and then going reflecting back in this direction BS. So now from the atom A, let's draw the two perpendicular line in AC, that is on the ray of QB, and another at the on the ray of BD. So these two perpendicular means here these angles will be 90, and this will also be 90. So the two refracted ray will be in phase or out of phase, depends on the path difference. So path difference here is, this is the path difference, this part. So when the path difference, that is CB, the path difference CB plus BD is a whole wavelength lambda, means is equal to lambda, or it is multiple of whole wavelength like n lambda. So then the two ray constructively interference to each other and produce the intense spot. So the condition, thus the condition of the constructive interference we can write as that CB plus BD, CB plus BD, this will be basically the n lambda. So this is the condition of constructive interference. So this is the condition of constructive interference. So from, if we now consider the triangle ABC, so let's say that this triangle, that ABC, so let us join this as ABC. So if we consider just triangle ABC, then we can write from this that sine of theta is equal to nothing but CB divided by AB. So we already know this AB, that is basically the distance between plane 1 and plane B, so is equal to CB divided by D. So if so, then we can once can write as that CB is equal to D sine of theta. So similarly from the another triangle, that is triangle this ABD, this triangle we can write this BD basically is equal to D sine theta in same way. So now we earlier written that CB plus BD, let's say this is our equation 1. So if we put this CB plus BD value in equation 1, easily we can get it 2D sine theta is equal to n lambda. So we finally get 2D sine theta is equal to n lambda. So n lambda is basically the path difference. So here the D is the interplanar pacing of plane, n is the n1, 2, 3 etc. stands for the first order, second order, third order reflection respectively. So these conditions is known as Bragg's law. So for as we derive this, that for getting the condition for getting the intense spot, that CB plus BD, this path, so you can see here that if we do this way, so it means this and this similar, so it will be in two reflected rays remain in phase, and constructive interference, that extra path difference CB plus BD must perfectly equal to whole wavelength or a multiple of whole wavelength. So that is basically n lambda. So now we are just this is the schematic for to prove the Bragg's law, and our famous formula is 2D sine theta is equal to n lambda. Here D is basically the interplanar pacing of the plane. Pacing of planes, and n is the 1, 2, 3, etc. So this ones means it is the first order, 2 means it is the second order, it is the third order. So there are various methods to solve this crystal structure, and device error method for powder crystal methods and all. So now just let us just talk about that what is the X-ray diffraction, XRD. So let it connect now the Bragg's law to real experiment. So in the XRD experiment, basically the X-ray source produces the monochromatic beam. Beam hits the powder samples, means if our sample is the powder, then it will hits samples, and detector rotates and measure the intensity versus angle. So the intensity versus angle means with it will be the angle will be 2 theta here, and the output hour is here XRD pattern, that is the intensity versus 2 theta. So there actually each peak corresponding to a specific crystal plane, and using Bragg's law one can find out the D value because we are getting the intensity with 2 theta value. Then we match the generally the standard database which are already available, and then we can identify the phase. So the phase identification is done if we do the XRD and apply the Bragg's law. So now how we can find out that from the D or lambda? This just few simple problems. First one is the spacing between principal planes of initial crystal is 2.82 angstrom. It is found that first order Bragg's reflection occurs at angle of 10 degree. What is the wavelength of X-ray? So yes, first we has to identify that what is given in our problem. So thus it is given the spacing between principal planes is 2.82 angstrom. So that means the D value is equal to 2.82 angstrom. So it is, and what is given else? Else given the first order Bragg's reflection. First order means here n is equal to 1, and then angle theta is given 10 degree. So it is always good to what are the given data, those may convert in SI units. So let's convert this 2.82 angstrom, that is basically in meter it will be 2.82 into 10 power of minus 10 meter. So now what is our formula? We know from Bragg's law that 2d sin theta, that is equal to n lambda. So here n is equal to 1, that means it is formula is lambda. So here it is asked that what is the wavelength of X-ray, that means has to find out the lambda. So we has to find out lambda is equal to 2 into 2.82 into 10 power of minus 10 meter into multiply with sine of 10 degree. So if you just do the simplification of this, ones can get it is basically 0.98 into 10 power of minus 10 meter. So this is our answer. So this is very easy way to finding the solving the problem. So let's move to another problem, that it is given that Bragg's spectrometer is set for the first order reflection to be received by the detector at glancing angle of 9 degree 10 minutes. Calculate the angle through which the detector is rotated to receive the second order reflection from the same phase of crystal. So let us first consider that lambda is the wavelength of X-ray. Wavelength of X-ray, and theta 1 and theta 2 the glancing angle for order 1, first order and second order respectively. So we can write this, that 2d sine of theta 1 is equal to lambda, and 2d sine of theta 2, that is basically second order, so 2 lambda. Here it is 1 lambda because it is order of n. So it is mentioned here that calculate the angle through which detector is rotated to receive the second order reflection from the same phase of crystal. So here we can see that sine theta 2 is, if we just simplify this both the equation, then one can get it that sine of theta 2, that is basically 2 sine of theta 1, or we can write sine theta 2 is equal to 2 sine of 9 degree 18 minute. It is given in the problem. So if we just simplify this, we can we just simply we can get it by simplification, that theta 2 is equal to sine inverse 2 sine 9 degree 18 minutes. So this is equal to basically 0.3232. So theta 2 is basically sine inverse 0.3232. So this will be equal to 18 degree 14 minute. So now if we find out the difference between theta 1 and theta 2, so basically theta, so now we can find out that theta 1 theta 2, let me write it red, theta 2 minus theta 1, that is basically 9 degree 30 minutes. So hence the crystal is rotated through an angle of 9 degree 30 minutes. So the angle through which the detector is rotated is twice the angle through which the crystal is uh, rotated. Therefore, the angle through which the detector is rotated from first order to second order, it will be just basically twice of theta 2 minus theta 1, that is 90 degree. So this is our final answer, that the angle through which the detector is to rotated to receive the second order reflection from the same phase of the crystal is nothing but equal to twice of theta 2 minus theta 1, that is 90 degree. So today is up to this. Thank you very much for watching this video. If you like the video, please click on the like button. Thank you very much.